Students, in this video, I am going to discuss steepest descent method. So consider the following unconstrained optimization problem, minimum of f of x, where x is a point in Euclidean space Rn. Okay, so n-dimensional problem. Now at any kth iteration, the next point is generally computed by the equation. So this is the general equation which is used in this steepest descent method. Xk plus 1 is equals to xk plus alpha k dk. Alpha k, xk is the current point, alpha k is the step size which is a positive scalar quantity, and dk is basically the search direction, a vector. Okay, so here is the equation. This is the current point. Next point is calculated, xk plus 1 is calculated with the help of this equation, xk plus step size and direction. Okay, so now the problem is to find out alpha k dk, because xk starting point is given to you, this is given to you. Aim is to find out alpha k dk. So since the gradient of a function f is the vector at a point x and denoted by gradient of f of x, this is a vector quantity for a given function, okay, which gives the direction of the greatest rate of increase in f of x. So this gives you the direction of the greatest rate, because we know that what is the meaning of derivative. Derivatives gives you the rate of change. Okay, similarly gradient of f of x gives you the greatest rate of change, increase in f of x. So it is orthogonal to the contour of f of x at x. This gradient of f of x is basically the orthogonal. This is orthogonal, that means perpendicular to the f of x. So if you will look at this, this is the contour of your function f of x, this is the contour. So gradient of f of x is basically the orthogonal. That's why if this is contour, this is the direction dk, search direction, then, or you can say that this is the tangent at any contour here, then obviously orthogonal means perpendicular to this. So this is delta f of xk. Now here delta f of xk either in this side or this side, perpendicular. So if you look at the values of the function here the function we have taken, suppose f of x is minus 3, here f of x is 3, in the next contour the functional value is 6. So obviously in this direction functional value increases, and in this direction functional value decreases. That's why this delta f of xk is basically the ascent direction, and this will be the descent direction. ये decreasing direction है, ये increasing direction है, based on these values. Okay, so this is denoted by delta f of xk, because here greatest rate of increase, that's why this is ascending direction and this is the descending direction. This is delta f of xk positive, and this is minus delta f of xk descent direction. Fine. Now for maximization, the search direction is simply the gradient. Why? Because this gradient is the increasing direction, that's why ascent direction. Hence for maximization problem, this is the suitable direction, and this is called as steepest ascent method. This method is called steepest ascent method. Now for minimization, the search direction is the negative of the gradient, that means this direction, and the method is called steepest descent. Here is ascent, here is descent. So this is, if you are following this direction, method is called steepest descent. If you are following this direction, then method is called steepest ascent. Okay, so now, so this is regarding the direction. So dk is called the ascent direction if in this direction, ascent direction, functional values increases. Here 10, here 6, here 3. So functional values increases in this direction. Hence f at xk plus 1 should be greater than f of xk, increasing direction. Now decay is called the descent direction if functional value is decreases. That means f at xk plus 1 is less than f of xk, decreasing direction. Okay, as our problem is minimization, minimum problem, hence decay should be descent direction. This is our feasible direction, descent direction. Hence f of xk plus 1 should be less than f of xk. What is xk plus 1? According to this equation, xk plus alpha k dk. So just replace it here. F of xk plus alpha k dk is less than f of xk. Now by Taylor series expansion up to order 1 we get. Now expand this. So this is the point and this is alpha k dk. So this is just like h, x plus h. So if you are following, for example, f x plus h, then what will be the Taylor series? F of x plus h f dash x up to order 1. Okay, now here in place of x we are having xk, in place of h we are having alpha k dk. Okay, this is equals to f of xk plus h is what? This alpha k dk, then f dash, in place of f dash, since this is a vector quantities, that's why we are having gradient of f of xk, and since this is the vector quantity, so there should be a dot, dot represents the dot product, and alpha is basically what? Alpha is the step length, a scalar quantity, hence you can take it outside. Alpha k is a scalar quantity, so you take it outside. So dk is the vector quantity, direction a vector, so dk dot delta fk. So this will be the Taylor series expansion. Okay, so now here we have this f of xk plus alpha k delta f of xk dot dk is less than f of xk. Okay, so because this is the condition, f of xk plus 1 is less than f of xk, so this quantity should be less than f of xk. Okay, this is cancel out with this, and hence we have this is cancel out. So alpha k gradient of f of xk dot dk should be less than 0, but step size is always positive quantity, so alpha k is greater than 0, so this implies this quantity should be negative. So this is the condition for descent direction. Now since that dot product is less than 0, hence gradient of f of xk should be perpendicular to dk. They should be perpendicular to each other. Okay, so now, and they are perpendicular to each other as well as their dot product is negative, hence we can say that dk, so dk should be minus gradient of fk. If we take this dk, then this will satisfy not only this condition but satisfy also this condition, hence then above condition fulfills. Okay, so then the method will be xk plus 1 will be xk plus alpha k, and this is the dk is this quantity. Okay, so xk plus 1 is xk minus alpha k gradient of f of xk. This is the steepest descent method. Now after selecting suitable direction, so we have selected the direction, but what about alpha k? So now after selecting suitable direction, aim is to find suitable steps length alpha k such that we get minimum of f of xk plus 1. So that means df by d alpha k should be 0 for minimum this, because now target is alpha k. So that's why differentiate this function with respect to alpha k and put it 0. So d by d alpha k, what is f? So here is f of xk plus 1. F of xk plus 1 is this quantity. So xk plus alpha k gradient of f of xk. Okay, so here is, this should be negative, minus, this should be 0. Okay, so now slope here is, if you take this curve, so at this point xk, this is the xk plus 1 point, so at xk slope is this decreasing direction, descent direction, this is decreasing direction. That's why gradient of f of xk dot dk should be negative, because this is the condition. This is the condition for descent direction. So this should be negative. So this should be descent direction नेगेटिव. तो ये डिसेंट डायरेक्शन है, यानी फंक्शन की जो वैल्यू इधर से घट रही है. ओके, यू कैन सी दैट मिनिमम इज समवेयर हियर. ओके, एंड दिस इज द डिफरेंस बिटवीन दीज टू इज अल्फा के स्टेप साइज. This is the direction, this is the step size. So here we are, our aim is to find reached at this place. So at this, what will be the slope? Slope is this gradient of f of xk minus, this will be minus alpha k dk. Since here we are using dk, here is we are using dk, so this should be plus, because dk is minus of gradient of this. I am not using here gradient of this, rather I am using dk. Okay, so gradient f of xk plus alpha k dk dot dk should be 0 based on this condition. In place of xk, here the point is xk plus 1. So gradient f xk plus 1, and k plus 1 is what? This k plus 1 is xk minus alpha k. In place of this we are using dk. That's why plus alpha k dk dot dk is equal to 0. Okay, so this is the condition. So thus d by d alpha k f of xk minus alpha k gradient f of xk should be 0. Okay, so now what is the way is just like this. If this is the contour, so we will start from here, we are moving in this direction. So this is the tangent, and this is the descent direction. So here, so this direction touches the contour here. This is the xk plus 1 point. Again, this is the tangential direction for this contour. So this will be the descent direction. So this will be the descent direction. So now this touches the curve next contour at this place. So this is the tangent for this contour, and this will be the descent direction. And finally we will reach to the x star. So this is the method. Okay, here if the contour value at this is c0, if the functional value at this is c1, if the functional value at this contour is c2, the relation will be c0 is greater than c1 is greater than c2. That means we are moving in the minimizing direction. Okay, so now algorithm. What is the algorithm? Algorithm is this. So step number 1, here set I is equal to 0. Take starting point xi, tolerance epsilon is greater than 0. Determine f at this point xi. Now step number 2, find gradient f at xi. The meaning of this is del f by del x1, del f by del x2, del f by del x, and this is a vector at point xi. Okay, step number 3, find xi plus 1 is equals to xi minus alpha gradient f of xi. We are using this equation. Here in place of alpha k we are using alpha. Okay, step number 4, find alpha for which f at xi plus 1, that means at this point, is minimum. Minimum means df by d alpha is equal to 0, because here we are using alpha in place of alpha k. Okay, इसका मतलब हमने केवल एक ही स्केलर का यूज किया, that's a total derivative. Okay, this is equal to 0. Now find xi plus 1, find xi plus 1 this point, and then functional value at this point. Okay, and then compare the value in the next here. Now compare. Step number 5, if f of xi plus 1 is less than f of xi, method is a success because our problem is a minimization. And if the magnitude of this quantity, the difference, the magnitude of this difference is less than epsilon, then stop. Else, if the magnitude is greater than tolerance level, then go to step number 1 with I is equal to I plus 1. That means go here, then find xi plus 1 gradient, this equation, next I plus 2 point, then again compare, then again find alpha, and so on. Okay, so this is the method. So now apply this method. So we are having this example, minimum of f of x1 x2 is equals to x1 square minus x1 x2 plus 3x2 whole square. Okay, here the starting point is x naught is 1 2, epsilon is 0 1 0.1. So starting point is x naught is 1 2. Gradient of f is what? So just partially differentiate this with respect to x. So this is basically what? Del f over del x1, del f over del x2. Okay, so this is the meaning. So what is this? Del f by del x1. Just partially differentiate this with respect to x1. So 2x1 minus x2. So 2x1 minus x2. Okay, this quantity. Now del f by del x2. So just partially differentiate this with respect to x2. We get minus x1 plus 6x2. So minus x1 plus 6x2. Okay, now this is gradient of f. This will be the equation. Xi plus 1 is xi minus alpha gradient f of xi. Okay, so now station number 1, I0, so x0 is 1 2 and gradient f of x naught is, just put it here, x1 is equal to 1, x2 is equal to 2, put it here, so we get 0 11. Okay, then f of x0, so f at x0 is at here, put x1 is equal to 1, x2 is equal to 2 here, so we get 11. Okay, so now substitute this and this value herein. So x1 will be, because I0, so x1 will be x naught minus alpha gradient f of x naught. X naught is 1 2 minus alpha, this is basically 0 11. So now first point is 1 and here is 0. 0 into alpha is 0. So 1 minus 0 is 1. Now here 2 minus alpha into 11. So 2 minus alpha into 11. This will be the point x1. Now find the functional value at this point. So this will be, put x1 is equal to 1 and x2 is 2 minus 11 alpha here. So we get 1 minus 2 into 11 alpha plus 3 2 minus 11 alpha square. यहाँ पर हमने रखा x1 की जगह 1, x2 की जगह 2 minus 11 alpha. So we get this equation. So this is a single variable problem, alpha. Alpha is the variable. So that's why df by d alpha should be 0 for minimum of f. So differentiate this with respect to alpha. So 11 minus 66, 2 minus 11 alpha is equal to 0. From here, alpha is 1 by 6. Okay. So what will be the point x1? X1 will be 1, 1, 2 minus 11 alpha, 2 minus 11 alpha is 1 by 6. So 1 by 6. After simplification, 1 and 0.166. This is the point. So now find the functional value at this point. So from here, put x1 is equal to 1, x2 is equal to 0.166. So we get 0.916. Okay. So now when you compare f of x naught minus f of x1, find the difference. So 11 minus this 11 minus this value. So 10.084, which is greater than this epsilon. Hence go to iteration number, next iteration, and for that I is equal to I plus 1. That means I is 0. So 0 plus 1 is 1. So now iteration number 2. What is x1? X1 is this point. F of x1 is 0.916. Now gradient f of x1 will be just here. Put x1 is equal to 1 and x2 is equal to 0.166. So 2 minus 0.166 here, and this gives you minus 1 plus 6 into this value. 6 into this value. So 0.996. After simplification, we get 1.834 and minus 0.004. Okay. Now x2. X2 is according to this equation, x1 minus alpha gradient f of x1. What is x1? X1 is this point, 1 over 1 or 0.166 minus alpha times this value. This value is 1.834 minus 0.004. So for 1 minus alpha into this and 0.166 minus alpha times this. So we get this equation. Now substitute x2 in this function. So we get f of x2 is equal to x1 whole square. So this value whole square minus x1. So this is your x1 into x2. x2 is this quantity. So this plus 3x2 whole square. So 3 this quantity whole square. Now for minimization, df by d alpha should be 0. Simplify this equation, just differentiate this and put it 0 and then get alpha. So what will be the alpha? Alpha is this quantity. So from here alpha is 0.50. After simplification we get alpha is equal to 0.50. Okay. So now x2 is equal to x1 minus alpha gradient f of x1. X1 is this quantity minus alpha we have evaluated and gradient of f at x1 is this quantity. After simplification point is 0.083, 0.168. So f of x2 is, just put it in the function, so we get 0.0776. Now when you compare f of x1 minus f of x2, this quantity is 0.8384, which is greater than epsilon, and hence go to next iteration. So next iteration x2 is this point, that means this 0.083, 0.168 transpose. F at x2 is this value 0.0776. Gradient f of x2 is evaluated with the help of this. So what we will get? We will get this minus 0.002, 0.925. Okay. Now compute x3. x3 is given by x2 minus alpha times gradient f of x2. So this is your x2 minus alpha times, this is gradient of f of x2. So this is gradient f of x2. After simplification we get this. Now put this value in the function. So f of x3 is this. Now differentiate df by d alpha is equal to 0 and put it 0. So after doing the calculation, alpha is 0.134. Now put this value herein. So x3 is 0.083, 0.044. Put here. So this will give you this point. Now f of x3 is given by, from this equation, put alpha की value यहाँ रख देंगे या इसको directly function में रखेंगे. So we get 0.0090. So now compare f of x2 minus f of x3. This will be given you 0.0686, which is less than epsilon. So stop, and hence x star is x3, which is this point. So this is the method of steepest descent method. Okay. So now here is the note point. What is the note point? Here you have two types of contours. One is the circular contour. This is circular contour. Second case is elongated contours for large. So this is elongated. This is stretched contour or elongated contours for large A. Okay. So now here in circular contour, descent direction is towards optimum point. For example, here this is the point here x0. So this is the tangential direction, and this will be the basically the orthogonal direction. So when you take the orthogonal to this, so you are moving in this direction. This point, this normal basically touches this contour at this point. So again draw the tangent, and then its orthogonal is this. So you will see that basically you are moving in this direction. Okay. However, here if you are taking this point, this is the tangential direction, then this is the normal direction. So you are moving in this direction, descent direction. So this basically touches this contour at this point. This is your x2 or x1, and then this is the tangent also for this contour. So draw the descent direction. This is the descent direction. This descent direction touches this contour at this point. This is your x2. Okay, then so you will see that you are moving zigzag motion. This is the, so descent direction is zigzag. So and this will take time to converge. That's why slow convergence. However, here descent direction is toward optimum point and fast convergence. So if your contour is circular, then we are getting fast convergence. If you are having elongated contour, then the slow convergence. Okay. Now the second note point, speed of convergence is related to the condition number of Hessian matrix, and we know the condition number for a matrix. We have already studied this in numerical analysis. The condition number of a symmetric positive definite matrix is the ratio of largest to smallest eigenvalues. Largest eigenvalue divided by smallest eigenvalue. Okay, so for a well conditioned Hessian matrix, the condition number is close to unity. Then the contours become more circular and the steepest descent method works best. Okay, so this will provide you the convergence. If your contour is circular, so you will get fast convergence. But how to decide whether the contour is circular or elongated? So you can decide this with the help of condition number. So for a well conditioned Hessian matrix, the condition number is close to unity and then the contour becomes more circular and the steepest descent method works best. तो आप कंटूर कंडीशन नंबर की हेल्प से आप उसका हेसियन मैट्रिक्स का बिहेवियर निकाल सकते हो एंड देन यू कैन डिसाइड द शेप ऑफ द कंटूर. Okay, now the third note. For the function, for example, this x1 square plus a x2 whole square, where a is in between 0 and 1. This is the Hessian matrix. Hessian matrix. So this will be, for this function, this will be 2 0 0 2a, because this is del 2f del x1 2, del 2f del x1 del x2, del 2f del x2 del x1, del 2f del x2 whole square. So this is the Hessian matrix. So eigenvalues are 2 and 2a. So condition number is the largest eigenvalue divided by smallest. So condition number जो आएगा वो आएगा a. So convergence is fast when a is 1. a is 1 जब होगा तो यानी a की वैल्यू 1 होगी तो क्या हो जाएगा x1 square plus x2 whole square. That means you are having this type of contour. Okay, so this is the meaning. So if somehow using suitable transformation we can convert the function f x1 square plus a x2 square in the form of some another function which is y1 square plus y2 square, then steepest descent method works very well. तो क्या ट्रांसफॉर्मेशन हो सकती है? x1 is equal to y1 and y2 is square root of a x2. So we get g is y1 square plus y2 square and the condition number is 1. Okay, so this will be the suitable transformation. Okay, now we are having another method which is Newton's method. We are having Newton's method. Okay, so from steepest descent method we have seen that negative of gradient point directly towards the minimum only when the contours of the function f is circular. Okay, so basically I think for today this is over. In the next video we will discuss this Newton's method. Okay, so that will be more fine. Okay, so we will discuss Newton's method in the next video. Okay, thank you.